Hi everyone, welcome to our first lesson on vectors. Before talking about vectors, it's worth reviewing the coordinate systems that you've seen already, including the 1D coordinate system, or the real number line, which we call R1. This coordinate system contains all real numbers, including whole numbers like 3, and negative numbers like -8, fractions, a half, a tenth, a third, transcendental numbers like pi, and then whatever random decimals you want to think about. They're all there. The next coordinate system you're going to come across is the XY coordinate system, where you plug an x value in. So x values are the values that run left and right, and you get a y value out. Y values are the numbers that run up and down. This 2D coordinate system, called R2, can be extended to R3. We live in a 3D world. We can move left and right, like the x direction, up and down, like the y direction, and forwards and backwards, which we'll call the z direction. The center, if you want to think of it that way, of all these different coordinate systems is the point 0. On the number line, that's the number 0. In the xy axis, it's called the origin, the point 0, 0, and in 3D, it's 0, 0, 0. Oh, and we'll extend this to 4D and 5D and 6D and higher. We'll keep going to higher and higher dimensions and keep drawing more horrifying pictures. Just kidding, we won't do that. The pictures stop at mostly 2D. We'll just do a few 3D pictures. We know how to graph points. If I tell you to graph the point 2, 3, you know it's important that the number that appears first be treated as the x-coordinate of the point. So that tells you how much do you go to the left or to the right. If the x-coordinate is 2, that tells us we move 2 units to the right. The second number is the y-coordinate. In this case, the y-coordinate is 3. That tells us to move 3 units up. The importance of the order of the numbers is referred to by this point being called an ordered pair. So we can't just interchange the x and the y randomly. It's important that the first number is the x-coordinate and the second number is the y-coordinate. And the reason it's important is it's to eliminate ambiguity. It's so that we can speak a common language to each other. In 3D, the first component is still the x, the second coordinate is still the y, and the third coordinate is the z. So x left and right, y up and down, z forwards and backwards. When we throw vectors into the mix, which are new geometric objects, it gets complicated for a few reasons. One of them is it introduces ambiguity, because up until this point, if you saw in brackets 1, 5, you would have automatically interpreted that as a point. Unfortunately, 1, 5 in brackets can also refer to something called a vector. Now, what is a vector and how is it different from a point? A vector has more in common with a line than it does with a point. It's called a directed line segment. It's a piece of a line. The beginning of that piece is always at the origin, at the point 0, 0 in 2D or 0, 0, 0 in 3D. The end of that line segment is at the coordinates indicated. So 1, 5 would mean the vector object ends at that point. We indicate the linear aspect of this object by drawing a line, or part of a line. So I'll start at the point 0, 0 and then draw a line. And then it ends at the point 1, 5. Now, this is just a line segment. To make it a directed line segment, we have to indicate what our ending point is. So we started at 0, 0, we're ending at 1, 5. So that's how we would draw the vector object as being distinct from the point object, even though they have the same notation. There's a few things that we do to reduce the ambiguity between points and vectors. One of them is, for points, we tend to use capital letters, like P, Q, and R. For vectors, we use lowercase letters, and we make them bold. But how do you bold when you're writing. Like I'm going to write a regular U, and beside it I'm going to write a bold U. How do I bold? Like, can I maybe just write over it a few times? And that was just a really messy U. So for handwriting purposes, it's better to use arrows. A U with an arrow above it, or a V with an arrow above it. And that's the predominant notation that will be used inside this course to indicate a vector. And then once in a while it's not clear, and that's largely going to happen when you're doing your homework in the textbook. If you're not sure, just send your instructor an email or post on the forums and we'll clarify. Okay, so let's put them side by side. The point P, 2, 3, so capital letter P, no arrow on it, doesn't look bolded, but it's hard to tell. It's indicated in red on the left. And here's the vector V, also 2, 3. I'll put the arrow above it because that's bold, but how are you supposed to tell? So there's the arrow just to reduce the ambiguity. These two objects are geometric objects in R2, but they're different. One's a vector, one's a point. Okay, first mini test of our definition of vectors, keeping in mind that order matters for vectors. It's an ordered pair, just like a point. We're asked inside this problem to label which vector in the picture corresponds to which vector defined algebraically in terms of the brackets. So I'm going to go not in order of the picture. I'm going to go in order of the stuff on the left-hand side. I want to first, and it also says if it's not there, draw it and label it. Okay, so let's see if the first one's there. 5, 7. I want to go 5 units in the x direction and 7 units in the y direction. So 5 units in the x direction is here. And I want to go up, so it's got to be B. Okay, so that one's done. Now 7, 5. I'll go 7 in the x direction and 5 up. Well, that's going to be C. Okay, next one. I want to go -7 units in the x direction. So that's 7 units to the left. And then I want to go 5 units up. Well, that's going to be point A, or vector A. Okay, and then 0, 8. So I want to go 0 units in the x direction, and then 8 units up, and we don't have that. So we have to draw it and label it. So starting at the point 0, 0, like all vectors, and we end at the point, at a y coordinate of 8, so we end at the point 0, 8. I'll give that a label. Our pictures here go from A to E, so I'll label this F. And then continue with the rest. Okay, the next one, 5, -7. So I want to go 5 units in the x direction and then 7 units down in the y direction. So that's E. And I'll cross that one out. And the last one, 8 units in the x, 0 in the y, that's going to be D. So not too bad in 2D. Now imagine trying to do that in 3D. Unfortunately, imagining having to do that is all you have to do, because we won't ask you to label a 3D picture. This is why. Okay, if I give you a pencil and paper and ask you to draw a 3D picture, the best you can do is what's called a 2D projection. You can use tricks to give the impression that it's 3D, and movies do this, and good artists can do this well. But as you can see, I'm not a good artist. This is my best I can do to indicate that the point 5, 8, 3 begins by going 5 units to the right, then 8 units up, and now 3 units towards you, like out of the screen. The vector is even worse. That's the vector 5, 8, 3. The sense of depth is not there. Now you can play games with see if I can get this to play. Hold on. Okay. So you can play games with 3D stuff. It helps you visualize. So there's In red is the vector 2, 3, 5. So let's see if I can orient it. Oh, it's so messy. I'm not gonna try too hard. I want to get the y pointing up. See, it's so horrible. Even with this stuff, it's horrible. But it's indicating how far do you go in each direction. That's the important thing. Being able to picture it, not too crucial. I think I've already messed up the vocabulary, but it's okay. It's not a big deal. For the sake of reducing ambiguity, points have the numbers inside the point referred to as coordinates. So the point 5, 6, we would say that the 5 is the x-coordinate and the 6 is the y-coordinate. Vectors, instead of using the word coordinate, we use the word component. So the vector 5, 6, we would say 5 is the x-component and 6 is the y-component. That gives you one more way to distinguish them. If you hear someone say the x-component is 3, you automatically can tell that they're talking about a vector. Another way that ambiguity can be reduced is to label, instead of using x's and y's, to label using subscripts, using numbers. This is particularly important if you're doing anything with code, anything with software, and if you're in higher dimensions. You start running out of letters of the alphabet. So the point P, instead of saying that there's an x-coordinate and a y-coordinate, we might say there's a P1 coordinate and a P2 coordinate. For a vector, V, instead of saying there's an x and a y component, we might say there's a V1 component and a V2 component. And for the vector U, there's a U1 component and a U2 component. It is confusing the first time you see it, but the more you work with this stuff, the more that you're exposed to it, the more value you'll see in this notation with the subscripts. It really clarifies, is this the first, the second, or the third part? Which vector does it correspond to? Is it the vector v? Is it the vector u? So there's a certain utility to having these labels, to adding these subscripts, even though it makes it look like scary math. And again, because the textbook uses bold and a few spots in the notes, I'm going to use bold, but for the large part, arrows. Arrows are the way to go, because hopefully you're taking notes and you're not taking notes with a bold, you're taking notes with an arrow. Throughout the course, you will see block definitions like this in the textbook and then in the notes. I'm not going to read them. You can read them out to yourself if you want. Usually the definitions are paraphrased in other ways, or they're drawn out, or they're picked apart piece by piece. So this definition shown here is the definition of a vector. And I've already talked about what a vector is. It starts at the point 0, 0, ends at some other coordinate. The components of the vector indicate the end coordinate of that geometric object. The number of components of the vector tell you what dimension you're working in. So if there's 3 components, you're working in R3, 2 components, you're working in R2. And that's all, and that's already there. This is just basically a summary slide. Now, I mentioned earlier that there's this so-called center of a coordinate system, the point 0, which can have a different number of coordinates. So in 2D, it's 0, 0. In 3D, it's 0, 0, 0. There's also something called a zero vector. It's 0 with an arrow above it. And the number of components depends on the dimension that you're in. Or in 2D, it's the zero vector is 0, 0. And in 3D, the zero vector is 0, 0, 0. We actually need the zero vector quite a bit. We'll refer to it with great frequency. two numbers to be equal to each other, it's fairly obvious. Like 4 is equal to 4, but 4 is not equal to 3. For vectors, the concept of vector equality is fairly simple, but not that simple. There's a little bit more to it. The first new thing there is for vectors that you don't have for numbers is for two vectors to be equal to each other, they have to have the same dimension. They have to live in the same space. So a vector in R2 cannot be equal to a vector in R3. It doesn't matter what the components are. It doesn't matter what numbers are there. They have to have the same number of components to potentially be equal. Now, once you've met that criteria, once you have that, the next thing is that their components must be the same. So the x component of one must be equal to the x component of the other one, and the y component must be equal to the y component. And if it's in 3D, the z component has to be equal to the z component. On the right-hand side is an explicit statement of this for two vectors in 2D, which we'll call u and v, with components u1, u2, and v1, v2, respectively. It can be said that the vector u is equal to the vector v if and only if u1 is equal to v1 and u2 is equal to v2. The statement if and only if is of crucial importance in mathematics. It means this is the only way it can happen. And if you see it, then it has happened for sure. It's bidirectional. That there's no alternative. If you want this thing to happen, if you want these two things to be equal, then the next condition must be met. And it also means if the next condition is met, it can't mean anything else. It must be the case that u is equal to v. So remember that if and only if, that's crucial mathematical language. Okay, simple test. U is equal to a comma 7 and v is equal to 5 comma b. We're told that these two vectors are equal. Find the values of a and b. So we're told that they're equal. So I'm going to write u equals v means that a comma 7 equals 5 comma b. So a must be equal to 5 and b must be equal to 7. That's it. That's the criteria that we need to impose in order for these two vectors to be equal. Two numbers are equal to each other or not. If they're not, that's it. That's all there is to it. But two vectors, even though they're not equal to each other, they can have a type of relationship with one another. There are actually several different types of relationships. So a connection, but not necessarily completely equal. One of these connections is something called collinearity. Collinearity is a fancy word that means they're on the same line as each other. So two vectors that are not equal can be collinear. Now it's a guarantee if two vectors are equal to each other, they are collinear. You would have come across a related word that we'll use as a synonym here, parallel. If u is collinear to v, then u is parallel to v. Likewise, if u is parallel to v, then u is collinear to v. So you can use them interchangeably inside this course if you want. I will. We can determine if two vectors are collinear to each other either algebraically, which you'll see later, requires something called scalar multiplication, or visually. So that's what we'll do here. We have three vectors indicated, the vector u, the vector v, and the vector w, and we're asked to draw each of them. And then after drawing them, we're asked to show that u and v are not collinear, but u and w are collinear. So I'm going to label the u in purple and draw it. It says move 1 in the x and 2 in the y. So that's our ending point. Draw the arrow to that point. A very good arrow. I may have to just call it a, I don't care, that's good enough. I'll label it with a u. Now the next picture over, I'll put in green, that's our v, 2, 1. V. And the last one I'll put in red, or maybe I'll use blue, 2, 4. So there's our vector W. So we did the first part, we drew them. Second part, show that U and V are not collinear. The easiest way to do that is to graph them together. So I'm going to graph the vector U in the second picture along with V. So 1, 2. They're not on the same line, not collinear. Now I'm going to draw the vector U on the third picture with W, because it asks us to show that U and W are collinear. So the vector U is 1, 2, so 1, 2, and I'll draw that in, and they are collinear. Yes, collinear. We'll see that there's another way, an algebraic approach, that's far less tedious, but perhaps not as satisfying as actually seeing it in the graph. We'll continue in the next video.